Hi, everybody. Welcome back to Dave's Math channel. This is my next installment of my new feature on my daily math problems, which I've been featuring on my Facebook group Classical Mathematics, which I visit regularly and try to post as many math problems as I can. I used to do them every day. That's what they're called, daily math problems. Now I'm a little busier, so I'm only doing them maybe every 2 or 3 days. But anyway, this was a problem that I first posted on July 28th. I came up with a variation of this problem a couple of days ago. Very difficult variation. This is the easier version. And what this problem concerns are quadratic polynomials, but in particular, random one. And what I mean by that is there the quadratic polynomials of the form x squared plus bx plus c. Sometimes you see a coefficient of a in front of x squared. Here I'm just letting a equal 1 for simplicity. And now b and c are random real numbers, but we're supposed to imagine that they're uniformly randomly distributed on the interval from minus L to L, where L is some positive real number. So anyway, that's the problem. I just told you the statement of the problem. Here it is written out again. And maybe one way you can think about this, we have this BC plane. There's a plane of possible solutions of B and C. They just lie in a square of length 2L centered at the origin. Oriented along the B and C axes. I don't know if that helps. But anyway, that's kind of the statement of the problem. But now the problem is two parts of this problem. We want to compute the probability, which I'm calling P of L, that both roots of f of x are real. So the probability kind of depends on capital L, the size of this square that we're defining our coefficients B and C to lie within. And then for part B, we want to know when P of L is equal to 2/3. So we want to find a specific value of L such that the probability that the both roots of this polynomial are real, if we pick B and C at random the way I just described, is equal to 2/3. In general, it's going to depend on L. So anyway, that's a statement of the problem. This might seem very confusing the way I've just explained it, but I think, they say a picture's worth 1,000 words. So, well, we'll get to picture in a minute. But first, we kind of have to, outline how we're going to solve this problem. So what do we know? When are the roots of a quadratic polynomial real? I think you probably learned this in high school. If usually you write the polynomial as ax squared plus bx plus c, and you probably learned the quadratic formula that says that the roots are minus b plus or minus the square root of b squared minus 4ac all over 2a. Well, that square root tells you whether or not the roots are real. I mean, if the thing inside the square root is negative, that means the roots are imaginary because the square root of a negative number is imaginary. And conversely, if the thing inside the square root is positive or zero, then the roots are real. If it's zero, there's one root. There's one real. We don't really care about that case because we're doing a random situation where the probability that it's equal to zero is essentially zero. But anyway, the thing you probably learned about the discriminant, the thing inside the square root is called the discriminant of the quadratic polynomial, and that usually sees written as b squared minus 4ac. So we know that if the discriminant is positive or zero, then the roots are real. If the discriminant is negative, the roots are imaginary. But in this case, a is equal to 1. So the discriminant is equal to b squared minus 4c in this case. And to say that the roots are real is just another way to say that is that the discriminant of b squared minus 4c is not negative, greater than or equal to 0. And another way you can say that is b squared is greater than or equal to 4c. Or the way I like to write this is I like to solve for c. c is less than or equal to b squared over 4. So I think you can see that the discriminant is positive if and only if this is true, if and only if c is less than b squared over 4. Well, this is kind of nice because the equation c equals b squared over 4 is just the equation of a parabola. Um, and what we're really saying here is that as long as we're below that parabola in the BC plane, as long as our solutions B comma C is below this parabola, then the roots are both real. Otherwise, they're both imaginary. So we want we want to calculate the fraction of the area of the square corresponding to B and C both being between minus L and L. That's a square of side length 2L. And we want to know the proportion of that square that lies below the parabola given by C is equal to B squared over 4. Okay, now I've just stated kind of algebraically what we're looking for. And like they say, a picture's worth 1,000 words. Here's a nice picture. So this blue parabola is just a parabola c equals b squared over 4. This is the BC plane, if you like. So x and y, we're using b and c here. And the parabola is just, that I show here is just a parabola, c equals b squared over 4. And as well as the parabola, I also show these three squares. The red square is just the square where L is equal to 2. So that's a square of a side length 4 because we're going from minus 2 to 2 in both B and C. And then the green square, we have L equals 4. So that's a square of side length 8. And then the purple square is a square going from L equals minus 6 to 6. In both B and C, that's a square of side length 12. And if you look at, I think this graph is really nice because you can kind of see what's going on. If you look at the red square, notice that the parabola intersects the red square along the two horizontal edges. And then for the green square, it happens to intersect the square at the two upper vertices. This is kind of a special case. And for the purple square, the parabola intersects along the upper edge. So we really have kind of two cases we have to consider. We don't really care about the intermediate case where L equals 4 because both of those cases should encompass it. So we're kind of interested in what happens when L is less than or equal to 4 and also when L is greater than or equal to 4. Those are two separate cases. So for the first case, the parabola intersects, like I said, the square along the two horizontal edges, and then we have to calculate the proportion of the area of the square below the parabola in that case. So the way to do that is first to calculate the area of the square. That's easy. That's just 4L squared. In each case, it's 4L squared. And then we also have to calculate the proportion of the area of the square in each case below the parabola. And one other thing you should notice is that in all cases, you always get that lower half of the square. I mean, if c is negative, we know that the discriminant has to be positive because the discriminant is b squared minus 4c. So we're subtracting a negative quantity, which is the same as adding a positive quantity. And b squared is always positive as well. So as long as c is negative, we know the discriminant is positive. That means that the quadratic polynomial will have two real roots in that case. So in each case, we can, the probability is at least a half. Is more than a half, actually, in each case. It includes the lower half of each square. So what we can do is we can add, 1/2 to the total area. The way I did it, I'm computing the areas of the fraction of the area of the square that's below the parabola. Anyway, let's just do the separate cases. So first, let's consider the case where L is less than or equal to 4. And like I said earlier, in that case, the parabola intersects the square along the horizontal edges. So we're going to get if we're computing the area of the proportion of the square that's below the parabola. You always get 2L squared for the bottom part. But then in this case, we're also going to get the proportion of the parabola that's below the rectangle of width 2L and height L squared over 4. Remember that the parabola has equation c equals b squared over 4, so when c is equal to L, that means when b is equal to L, that means that c plus or minus L, that means that c is equal to L squared over 4. So we have a rectangle bounding the upper portion of the square that's um, you know about that contains the parabola, the parabolic region. And another thing I should point out, yeah, you actually have to use calculus to prove this. I'm not going to do it here. But whenever you have a parabola bounded by a rectangle that encloses the whole parabola, as long as it's symmetric. So in this case, we have a parabolic region of height L squared over 4 and width 2L. So we know that the area of that bounding rectangle is just 2L times L squared over 4, or if you like, L cubed over 2. But then the fact you have to know, which you can derive easily from calculus, is that the area below the parabola is exactly 1/3 of that area. So that would be L squared over 6 in this case. So that's what. So the area below the parabola. That's the area, the proportion area in the upper half of the square that's below the parabola. That's L squared over 6. But then we have to add 2L squared to that because that was the proportion. That's the area of the lower half of the square, which contains all the solutions we want. So the total area we have here is 2L squared plus L. Actually, it's L cubed over 6. So I made a mistake. Yeah, because the height is L squared over 4. So we're going to get L cubed over 6. So we get 2L squared plus L cubed over 6, which if you simplify that, you get L squared times L plus 12 all over 6. And now we have to divide that total area by the total area of the square, which is 4L squared. And if you do that, that's equal to P of L. And if you simplify that, you get L plus 12 over 24. So that is the formula for P of L when L is less than or equal to 4. Well, that's nice. So now we got one formula we want, but we still have to do the other case where the L is now greater than or equal to 4. Both cases should agree when L equals 4, and they do. But in the second case, remember the second case is where the parabola intersects the upper edge of the square. In that case, we're going to get we're still going to get the entire lower half of the square without areas 2L squared. I probably didn't do this in the most efficient way possible, but you're going to get actually 4 regions we care about in this case. So we have the lower half of the square that has area 2L squared, but then we also have 2 rectangles on either side of the parabola. You have these 2 rectangles in the upper half plane, the upper half of the square. I didn't draw them here, but you can imagine a rectangle. If you look at the purple square here, you've got a rectangle going from the point where the parabola intersects the upper edge, and then you could just draw a vertical line down from that, and that gives you kind of a thin rectangle. And I think you can see if you look at the rectangle on the right. I mean the point on the value of x where the parabola meets the upper edge of the square is equal to 2 times the square root of L. Uh, if you do the math, you'll just see that's true. And so we're going to get the values of x along this right rectangle are going to go from 2 times the square root of L to L. And then you get the same thing for the one on the left. So this one's going from minus L to minus 2 times the square root of L. So when you do all that, you're going to get two rectangles with each with width L minus 2 times the square root of L. But then their height is equal to L, and we have two of them. So their total area is going to be 2L times the quantity L minus 2 times the square root of L. I know that's kind of messy, but that is the area of the rectangles. Finally, we have a third region. Our fourth region we have to consider, and that's the region below the parabola. But this is kind of like what we did for the other case. In this case, the height of, there's a bounding rectangle for that region. The height of that bounding rectangle is L, because we're going from the c-axis, if you like, the horizontal axis to the upper edge of the square, whose height is L. So the height of this rectangle is L. The width is 4 times the square root of L. Because remember the values of x where the parabola meets the upper edge are plus or minus 2 times the square root of L. So you're going twice that distance, that's 4 times the square root of L. So we've got a rectangle whose height is L and whose width is 4 times the square root of L. That's going to give a total area of 4L times the square root of L. But we have to divide that by 3 for the same reason we did before, because we're doing a parabola whose area is 1/3 of the area of the bounding rectangle. So if you add all these factors together and simplify, you get 12L squared minus 8L times the square root of L all over 3. And that's the total area we want. And now we still have to get P of L, we have to divide that by 4L squared, the area of the square. And if you do that and simplify, you get 1 minus the fraction 2 over 3 times the square root of L. So that's the second formula you get. So to summarize, P of L is given by two different formulas depending on whether L is less than or equal to 4 or L is greater or equal to 4. If L is less than or equal to 4, you get L plus 12 over 24. And if P is greater than or equal to L, you get 1 minus 2 times 2 over 3 times the square root of L. And you can check for yourself that when L equals 4, it's pretty easy to check. You just plug in 4 for L in either of these formulas. You're going to get 2/3 in both of those cases. So the answer to part B is P of 4 is 2/3. When L equals 4, you get 2/3. And that's the only value of L that gives you 2/3. P of L is a monotonic function. It monotonically increases with L. I think it's pretty easy to see that as L goes to infinity, P of L is going to 1. Another way of saying that is if you let B and C be really large, then it's almost virtually certain that you are going to pick a quadratic polynomial with both of its roots real. In the limit in which L goes to 0, the probability goes to 1/2. Remember what I said? It's always going to be, the roots are always going to be real when C is less than 0. Might be a good idea to go back to the picture again. Yeah, remember what I showed you? So if you kind of look at this red square, if you made that red scale get really, really small, basically all you're getting in that case is the lower half of the square. So P of L will approach 1/2 as L goes to 0, but it approaches 1 as L goes to infinity. In the kind of intermediate cases, L equals 4, where it's equal to 2/3. So anyway, that completes the problem for today. So thank you for watching. Long live math, and I'll see you guys next time.